Hello, University of Lancashire, and welcome to the CMS control room.
I will be the underground guide for today. I'm Derek Grove. I'm a PhD student based here and working on the CMS experiment.
And my name's Claire. I'm a South African working here at CMS, and I will be up here in the control room so that we can liaise with you and you can ask as many questions as you want about CMS. So yeah, shall we get going with the underground tour? Is anything else you want to start, let's say?
Well, I just wanted to encourage everyone to ask questions. Don't hesitate to interrupt us at any point if you have a question. We actually prefer that, and it helps us kind of tailor the experience to explore the things you're most curious about.
Yeah.
Because we have kind of a vanilla tour where we will show you everything, but if you ask questions, we can really teach you more about what you might be curious about. So yeah, I'm going to get my safety gear and we're going to start heading underground, and Claire will be here to run the show.
All right, excellent. So yeah, like Derek said, we are definitely, ask as many questions as you want whenever you want, and we will try to answer as many of them as we can. So yeah, so we are here in Cessy, France, which is what we call point 5 at the LHC. So the LHC, as you probably know, is this 27-kilometer long underground ring of magnets where protons are accelerated to 99.99991% the speed of light. And at 4 points around this ring, the beams of protons are brought into collision. So the beam line in most of the LHC, there are 2 separate beam pipes held under vacuum. And so the protons, there's a beam of protons that go around clockwise, and then another beam of protons that go around anti-clockwise. And for most of the ring, those 2 beam pipes are completely separate. However, at 4 points around the ring, the beam pipes are combined into 1 beam pipe, and it's in the center of this, thanks to magnets that allow us to squeeze and focus the beam. The beam of protons cross over, and that's where we can have collisions happen between the protons. Now, at these 4 points, obviously, we want to see and discover and find out what is happening when those collisions happen. So around each of these 4 points, we've built these big particle detectors. And there are 4 of these. So Atlas and CMS are general purpose detectors. And then we have Alice and LHCb, which are kind of specialized detectors so that we can do a range of different types of physics at the LHC. Derek, what are you up to?
Hey, so we're going to show this real quick, but this is how we enter some of these restricted access areas. To get to the underground, you have to pass through this very special door, and you have to have your own personal dosimeter. And so this measures any potential dose of background radiation that you may receive while in any of these areas. We will receive 0, but still, it's part of the safety. So I have to scan this, and then I will enter this room. The doors will shut me in that tiny box, and then I have to scan my eyes with the black box there. And my retinas have to match the biometrics connected to this dosimeter, and then it will let me through to the elevator and to the underground area. So let's do this. Hello. And it also scans to make sure I'm not smuggling anything in with me. And hopefully that doesn't fail. Okay, it passed. So now it'll scan my eyes. And I'm through. And now Naomi will do the same and kind of give you the POV of going through this system. Now she actually does have to smuggle the camera. If you're bringing tools or other equipment with you, you need to take that through a special door. So you're not supposed to bring things through here, but the camera is okay and approved by CMS Safety. So we're now going to take the elevator, and we're probably going to lose internet. So Claire can take back over, but this is always fun to point out. The magnet is on underground, and so there's a warning light. But yeah, while we wait for the elevator and then ride it, we can give it back to you, Claire, in the control room.
Thanks. Yeah, so they are going to be going almost 100 meters underground to where we have our experimental cavern that houses the detector itself, as well as we have also next to the experimental cavern, we have service cavern that has equipment, for example, for the data readout, for the triggering, and all of that. So yeah, do we have any questions at this point in the room? I don't know, Catherine, do you want us to like what's the plan for doing questions? Are you gonna get people to come up?
So I think if anyone has a question, could you raise your hand?
Okay.
Okay, so we have some pre-submitted questions as well.
Oh, cool.
So I can just ask on behalf of the students a pre-submitted question.
Sure. Yeah.
So yeah, one of the questions we had was what involvement does CERN have with quantum computing?
Ooh. Okay, not really my area of expertise. However, there is so part of CERN obviously is the IT department, and there is, as far as I know, a quantum computing initiative there. It's mostly in terms of research at this point. So yeah, just trying to really understand how things like how the quantum computing works, not necessarily going for pragmatic approaches or uses for it, but it's more of one of these open-ended like research type of areas. Which I think is lovely because this is exactly what we do here at CERN, right? It's a research laboratory. The point is not necessarily to find a practical use for something. The point is to understand it, and then once we understand it, then these opportunities kind of organically come from that. So Derek is underground right now. What are we looking at?
So we just got off the elevator and we had to play with our connection, but we have good signal down here. So basically, we're going to try to show you with the camera, but what you might see is all these flights of stairs that in an absolute emergency, and I say absolute because in a normal emergency, if there's such a thing, you would take the elevator, but these stairs are still here, of course. The elevator has its own oxygen and power supply, so that's why in a regular emergency you take again, who knows what a regular emergency is, you would take the elevator, but these stairs at least can show you why we prefer to take the elevator, because you would not want to run up all of these flights of stairs to get back to the surface. The light is just a fun little demo to demonstrate that data goes back to the surface after we collect it down here from the experiment. But yeah, we are pretty deep underground, but it's also very spacious. And then we're going to go through the service cavern here and show you some of the electronics that are related to the readout of CMS. I like to think of it almost as like the brain of CMS. People may argue with me on that, but the idea is in the experimental cavern where the detector is, it's a lot of sensors. That is what the detector is, particle sensors, particle detectors. But a lot of the logic needs to be done outside of the detector and kind of in this room. So logic for what events we want to actually record and save is done by the trigger system. And so a lot of the electronics related to the trigger can be found in this room. And the electronics, for any of you that are tech savvy, we have a lot of FPGAs in use here. The FPGAs do a lot of very quick logic for us, faster than a traditional CPU could do. And since this is a virtual tour, we can actually walk up and down these rows and show you some more of these electronics, but also some of the wiring and the cooling, all of this pretty neat cabling. Yeah. And so as we walk down these rows, you'll also see some of these cyan colored cables like you see right here. Now, these are actually fiber optic cables, and they, at least the ones to the pixel, I'm very familiar with. But yeah, so some of the data, majority of it coming out of the cavern is coming in on this fiber optic cable. And we're going to keep walking around here. Again, if there are any other questions, we can take those while we're kind of doing this.
Yeah, so
But,
maybe I can also say, so the
yes.
detector itself is made up of multiple different sub-detectors, we call, like, so we have right in the center of the detector for tracking purposes, we have two different tracking detectors. We have a pixel tracking detector and a silicon strip detector. Around that, we have two different calorimeters, and then we have four different muon systems. And each of these detector systems are built completely separately, so they can run themselves as their own standalone detector. But that also means that the readout system for them is completely different. For example, just comparing pixel to tracker, the pixel is fully digital. The tracker actually still reads out analog, and then the boards convert that signal into a digital signal. So you have all of these different types of signals in all these different types of ways coming together off the detector that then need to go and be combined and put together into one like unified data format. And this is done by the central data acquisition system. And there, and so, just everything, like all the systems are different. Just because Derek knows pixel does not necessarily mean that he would understand how the tracker works, for example, and vice versa, because I'm a tracker person. So yeah, like it's just really, really interesting because of like how many differences there are, and then how we are able to combine them all together to give us, the data that is coming out of
Be
this
very careful, high voltage is on these racks.
Yes.
There is a yeah. You see, even though we're allowed to walk around when there's like a red barricade, we don't pass the red barricade.
Yes, we know our limits. So we're going to continue now into the experimental cavern, but there's a few things to see along the way. There is this guy, I'll briefly mention some more safety equipment we have here. When you're entering certain areas in the underground, if there's a risk of oxygen deprivation, like from a gas leak or a fire, you have to carry one of these with you, but it doesn't look like this. It looks more like this. So it's all packaged up neatly in this container. It's called a self-rescue mask, and you have to go through this training where they actually simulate a emergency in like the tunnel, and you have to be able to put it on while they're watching within 30 seconds and evacuate, something like this. But it delivers oxygen for up to 30 minutes so that you can have ample time to get out of the area that's having some emergency. So you breathe in and out of this bag, and it converts your exhaled air, your CO2, back into some appropriate amount of oxygen to keep you alive. This is the door that leads to the LHC tunnel. And so, of course, we can't go in the tunnel. I've never been in the tunnel, but I hope someday. But just know it's through there, and it would look like this. We have a picture on the wall to show you if we could go through.
We've got the picture. Oh, there we go.
Oh, you also have the picture. Yeah.
We've got the schematic up. But yeah, that's what it would look like if you went into the tunnel.
Not this very nice picture.
Yes.
This is a great selfie spot in case you ever come to visit.
Yes. So you can make it look like you were in the tunnel for a picture. But
yeah. So the tunnel, like the different access areas are controlled by different people. So everything to do with the tunnel is controlled by the LHC accelerator team, whereas we at CMS control our access areas. And going through that red door is going from a CMS area into an LHC area. So it requires a completely different set of accesses. But Derek is going through these yellow pad doors. What is it?
So this leads to the experimental cavern of CMS. So I have to do the same procedure where I enter. It will scan my eyes. And now it allows me through to the other side. And in just a moment, yeah, we'll see CMS.
So the way that the access requirements work is they put the maximum restrictions going in, but then you can always exit without any restriction at all. Obviously, you know, in an emergency, that's ideal. You get out as soon as possible, and then you badge yourself in at the surface to let the system know that you are out and safe. But they want absolutely no restrictions or anything that could delay you when if you need to evacuate. But they also make sure that only people who have done like the correct training and stuff are the ones who are able to get into certain areas. Oh,
Do we
the iris
have?
scan going on?
Yes. So it caught her the first time trying to bring the camera in, but she got through the second time. So we actually have to do a little maintenance to our gimbal here to switch to a more manual thing. I think we had mentioned, but there is a very strong magnetic field inside the experimental chamber. It's from the superconducting solenoid that we have in the CMS detector, and it permeates, that magnetic field will permeate pretty much the entire experimental cavern. And actually, we're in its influence right here, a bit away from the detector and the cavern. But once we're in there, it really messes with our camera equipment. So we have to switch how we hold the camera before we enter. So we can take more questions, though, if there's any. The quantum computing one was, I only heard half of it, but yeah.
Oh, it was a pretty tough question.
Yeah, it is. It's not a question I'm prepared to answer either, but.
So if anyone has any questions, can you raise your hand? Yes, Ado?
Oh, I don't know if you can hear me. My name is Idori. And I want to ask about the LS. When Petri was presenting, one of the benefits was to the common man, not for the researchers and everyone, is that we had World Wide Web. We also had those for medical imaging. And to me, I'm in computing, and I think that both of those came from engineering, not from the process of LHC. So, and we've been told that these protons are fired at almost the speed of light, around a 27-kilometer radius, or circumference rather. My question then is, what really is the value of these to the end man? And what is, and we have also been told that if there's a plan going in place to increase this to about 100 kilometers. And I heard about the Higgs boson. I hope that's not the value, because what are we benefiting from firing these protons at that speed and then colliding, and what is it for us? Because I don't think that the imaging processes and the World Wide Web were part of that. I think that's the engineering factor. And what is the benefit that will accrue if we extend this to 100 kilometers? Thank you.
Okay, that was some excellent questions in there. So if I understood, it was a little bit hard to hear at the start. So we're asking specifically what the benefit of the LHC is, and then the extension of the LHC to the FCC, which would 100-kilometer long one. So
I know.
I think that first of all, we have to remember that all of these medical applications that you mentioned come not because somebody thought, oh, let's build something to use for medical imaging or for cancer therapy. It came because humans were like, oh, I would like to understand how the universe works better. How am I going to do that? Oh, what if I smash things together and see what happens? And so people did research for research's sake, and a byproduct of that was the development of these technologies, which have then gone on into the world. Now, most particle accelerators are found in hospitals. The magnetic, like magnets, and are used in the imaging. The tracking detectors that we use to build our detectors are now are being used in medical imaging. We have the Medipix, which, you know, it's like it can produce these incredible color X-ray images, which are absolutely incredible. So whenever there's something like this, you have to be able to kind of let research kind of run free and run creatively, because that is because it's that creativity that gives us all of these this feedback into society. And I don't know, I'm not sure if you mentioned it, but like proton therapy is an amazing type of cancer therapy, because it's like a radiation treatment, but the difficulty with normal radiation treatment is that because you're shooting gamma rays, you don't have as much precision. So if you have a tumor like on a brain stem or something, the benefit of using protons, because they're charged, is you can get a much more precise focus on on these things. So that is really like what we've got as a result of just people wanting to do fundamental research and building the LHC and previous accelerators and particle detectors. Like so many of the detector technologies, like I said, have moved on into the world. I'm going to pause that question on the FCC, and we're going to come back to that in a little bit. But Zoltan wants
yes,
to say
I would
something
like
here.
to add one more thing. What concerns the basic research itself, it is very hard to tell when and if at all it will have an everyday use of in the society. But let me bring you an example that was not expected by anyone. About 100 years ago, when Albert Einstein made the general relativity, which is extremely abstract with a mathematical formalism that it is extremely hard to understand, I couldn't manage. Then nobody thought that at any day it will have a practical use. It was very hard to prove that it works that time. As the years went by, we saw more and more justification of this theory, and at some point in the 80s, it struck as the thunder struck from the sky that this is necessary to correct the results of the GPS satellites. Otherwise, it would be completely useless. So what I can say that totally unexpectedly, the general relativity is in your pocket today.
Yeah.
That's a very important thing. So that's
and quantum mechanics,
exactly. So these two things underlines that whatever we do today, and we don't see the practical use now, might have something in the future, and it is impossible to predict how and when.
Yeah, I think what I always tell people, like politicians and stuff, is fundamental research is something where you can guarantee that you will get an outcome, a positive feedback, it's a positive investment. It's something that you will get a return on investment from. Can't tell you what that investment will be, and we can't tell you when it will come, but we can tell you that there will be a positive investment. And that is very different to a lot of other investments where, they can say, okay, in 6 months, you can have this, or you can have, negative, right? So they can give you time, but it's like the Heisenberg uncertainty principle of like fundamental research applications.
All this funny stuff that we learned at the university.
Yeah. Derek, let's go. I don't know if there's anything else what you want to say there, but why don't you tell us about what you're up to?
Yeah. Well, I don't want to add anything to that question. That was a good question and also great answers. I think everything's covered, and we'll come back to the FCC question. But we very much want to show you this thing behind me, which is the CMS detector. So I hope you can tell through the camera, it's very big. We're about positioned somewhere in the middle because we're up a couple flights. And then I also am holding this magnetic chain. Well, it's made out of some sort of magnetic material, but since we're down here in the cavern with the strong field,
Hey.
It just
Wow.
totally is attracted to the field. It wants to align itself with the field, even this far away. And so it's very like freaky playing with things in here that are magnetic.
We
And-
have to remark here that the field that Derek and his famous magnetic field indicator chain sees is about 1 per mil with respect to what is inside the detector, and totally harmless.
Yeah.
Yeah.
So the point of
So-
having a magnet is to bend the particles that are coming outwards from the collision point, because if we bend them, first of all, we can tell if they are positively charged or neutrally or negatively charged, or even neutral, because they would go straight. But the other thing is, if we know the strength of the magnetic field and we measure the curvature, that gives us a measurement of the momentum of the particle.
Yeah, I like to think of it, that's all correct, but to me, it almost seems like a hack. If you do these particle physics experiments in a strong magnetic field, you get the charge identification and the momentum measurement for free, basically.
Yeah.
If you were to do it without a magnetic field, the charged particles would move in straight lines. You'd have to have some other way to identify the charge and the momentum. So why not just build a gigantic magnet and then do the experiment in that field?
Plus,
So-
it's super fun to have a
It is
super
very-
strong
yes.
magnet.
So yes, so we're gonna move, we'll actually go closer to the detector, but maybe we go up top first, actually, and show you
Cool.
from here.
So I mentioned earlier that the detector was built in these different, like all these different layers, right? So right in the center, we have the tracking detector. And the tracking detector's goal is to allow the particles coming out of the collision point to travel through the tracker with as little disruption as possible. And there's the tracker is made up of lots and lots and lots of layers with extremely high precision. And this allows us to measure the position of these particles. It's like a join the dots game. You know, we get like a little signal, ding, 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 as the particle moves. And then our software system goes and reconstructs this curved track. Once the particles have moved through the tracker, so now because we have the track, we have the curvature, we have the magnetic field, we can get the momentum. Then we want to measure the energy of the particle. And to measure the energy of the particle, the way we actually do this is by stopping the particle and measuring the amount of energy that particle lets off as it gets stopped. So imagine driving a car into a brick wall, bam, the bricks go spraying outwards. You see how many bricks got scattered, how far they got scattered. You add that all up. That gives you an idea of how much how much energy you in the car had. So it's the same thing with a particle. We stop them in these calorimeters, and when we stop them, instead of a spray of bricks, we get a spray of light. So that, and then we measure the light. That tells us how much energy the particle had. And then we have muons who manage to get all the way through our calorimeters. They don't get stopped in the calorimeters. So around the outside of the detector, we have muon specific detectors, which are basically like really big tracking detectors to catch these muons as they travel through. And so we can tell if something is a muon if we've got tracks on the inside and on the outside of our detector. And I think that is what we can see from up here. Is that right, Derek?
Yeah, so basically we are up above, well, not completely above the detector, but what you see here may be related to the pictures, this big red, what shape is that? And it's not an octagon, is it?
Something
No,
about
this
1,
is-
2, 3, 4,
Oh,
5,
12,
6,
12
12
It's a 12-agon. So this big red, that's the,
Dodec.
No, isn't that 20?
No,
I don't know.
the
Duo
chi
I don't know.
Okay, Pentagon.
12 it's 12
So, on the other side of that, it's a giant steel plate, but just on the other side of that is where you would find some of these muon detectors. And then also, you may be wondering why we have such a strong magnet in the middle of this thing, a superconducting solenoid. You may be wondering why parts of the structure are built out of a magnetic metal like steel. It almost seems like
red stuff that we are showing you.
So it almost seems like a design mistake, but actually it's very intentional. So the field inside the solenoid is 3.8 Tesla. It's very strong. And if you've done your physics classes, it's a constant magnetic field inside the solenoid. On the outside, the field would fall off rather rapidly unless you were to put pieces of steel or some other magnetic material around the solenoid, that then they kind of trap that magnetic field almost and keep it stronger, closer to the solenoid. And so this is what we're trying to do. We're actually building like this container of the magnetic field to keep it strong inside our CMS detector. So it's strong, it's strong outside of the solenoid, but still inside of the CMS detector, if that makes sense. We have those muon subsystems outside of the solenoid. And it's 2 Tesla, I'm told just now, outside of the solenoid, but still very strong. And we need that to curve the muons.
Yes. Sorry, yes.
That's all I have to say. But I will point out, so where is the beam? Where does the proton beam come from? It's actually, the beam pipe is inside this orange material, and this is an absorber. So you'll have these, as I understand it, correct me if I'm wrong, you have these accidental, minor collisions up the tube, up the beam pipe, because maybe a proton kind of escapes or something and hits the edge. But that could create some shower this way. And we don't want that getting into our detector and interfering with our measurements. So we have this absorber material here to try to absorb those and mitigate that. So the beam pipe is inside this material, and it of course goes directly into the middle of our detector, and that's where we want the actual collisions to occur, is in the very center of our beautiful CMS detector.
But what we have to remark here, that the detectors are like pearls on a necklace. But the necklace is the LHC. We don't have anything common with that, except that we are sitting on like a pearl on a necklace.
Oh, I see what you're saying. Yeah, right. Yeah. So the beam pipe goes straight through the center, exactly. And the beam pipe is under vacuum, but none of but outside of the beam pipe, there's obviously not vacuum, and the particles. So what happens? The protons will collide in the center there, and then fly outwards. So whatever the remnants of the collision fly outwards from that collision point, and they exit the beam pipe. The beam pipe's only like a couple of centimeters wide, so the particles exit the beam pipe and then fly through the detector. So yeah, this is a nice event display that we have up on the screen here, showing a collision at the LHC inside CMS. And you can see where you have these big green and blue blocks. That's basically a histogram. It's showing a spurt of energy being left in the calorimeter from some or other particle. And you can see these 2 red lines, which are muons that have come out of that collision. And that one in the back, you can even see like you can see the red layers of the muon detector that got triggered as these muons passed by. So this could be, for example, a Z boson decaying into 2 muons.
I think it was a Higgs couple.
You think Higgs to mu mu? Ooh, nice.
Mu plus EE.
EE mu mu. Okay, so Higgs to ZZ. Yeah, cool.
Practically.
Cool.
Well, at least.
Oh yeah, there we go. The green lines. No, you see, this is like
Usually we don't look at these plots, or only
Right,
very
right.
rarely.
Yeah,
That's
when
why
we're doing
we
the
are just-
data analysis, it would not make sense to look at events, you know, by eye like this. We do a lot of data analysis, and we troll through the huge amounts of data that we have. But if we have an event that I'm just getting distracted
this
by
is usually
Derek
what
there.
happens when we allow the guy to go in the magnetic field.
It's
We
so cool.
completely lose it.
Yeah, look at
You see?
that. Like
So
you're
we
making
are-
some artwork there, Derek.
Yeah, yeah. So we're, standing right beside, so on the side of CMS. And so you have to kind of imagine what the field direction might be here, because it's going to curl around the solenoid. It's also influenced by all that steel, so it is a bit hard to kind of imagine. But I'm pretty sure around here, the field is kind of pointing this way a bit, maybe perpendicular since we're on the side.
Hmm.
But then you can
Cool.
see this chain it really just wants to go.
Yeah.
That way. So it's very cool. But this is also a good opportunity. We can walk up and show you the slices again. We talked about how this is constructed. And
Actually,
Claire,
I'm
you
not
can
sure if
narrate.
we did.
Did
So
we?
we talked
Ah.
about the layers, but so in addition to the layers of CMS, the detector was also built in slices, 15 slices, if I'm not mistaken.
Yeah, we can
Yeah.
negotiate.
We can. So you can imagine, if you imagine like a Swiss roll, for example, that then you slice into slices of Swiss roll. That's
Salami.
kind of what
Salami.
Swiss roll is much nice. It's cake.
On the
Cake
other
has
hand, I come
layers.
from a country where the salami is.
But salami doesn't have layers, and cake has layers.
Well, you eat both.
But the benefit of this was, in fact, the entire detector was actually built above the ground. And then the slices, once fully constructed, each slice was lowered down one by one, down this 100 odd meters
They are
from the
just below
surface.
that.
And we can show you that hole right now that it was lowered down. It's a
And
bit
then-
ominous when it's all dark, but
The heavy, yeah, so there's a
Yes.
lid right now on because we're getting ready to close up. But I think the heaviest slice was something like 2,000 tons. And you can just imagine the logistics. Like this is a unique piece of equipment that, nobody else had built. So you can imagine how the physicists were holding their breath as each slice, came down this 100-meter long shaft.
Some bottles of champagne popped.
A few, yeah, at the end of it all. So yeah, Derek is now right on the floor of the cavern.
and you can, and we're going to show you the slices here.
There we go.
It's more
Cool.
obvious to see that these are, cut.
You can really
Through
see
here.
through.
Yeah, so just from like a building and a logistics point of view, this is truly incredible. And
But also all our cables come through these slices from the detectors. Otherwise, we would not be able to cable them up.
yeah, so like all the inner bits still have to have power and cooling and all that stuff.
Just to
Look at
mention that in this configuration, we have 120 million data channels.
right?
Each needs to be read out. Each needs to have a power supply. Some of them needs cooling, some of them gas, different cooling.
There you could see some of these electronics and piping and everything going on here. It's just
It's very
super
complex.
cool.
It's more complex than a submarine fleet.
Yeah, and again, each layer of the detector is built individually, but then we also have to have teams of people working on the combination and the integration of all of these into one thing that works. So how would you can you show us the feet? I see we can see these orange feet
Yes.
there. So for example, if we do want to, we can move these slices apart, right?
You can see the wear on the ground. We do have a system to levitate it or pick it up as best we
That's a
can.
hovercraft.
But
It's
even then-
basically a hovercraft. Yeah. These
So
orange
you
things.
have pressurized air, and you can tell them the PSI. I don't know. There's some
A lot.
a lot of
Lots of
PSI
PSI.
to kind of get some airflow and create this cushion of air that then we can use this massive cable back here.
So practically you
Then
reduce the
yank on it.
you reduce the friction practically to zero.
Mm.
And that's
Well,
very important.
not exactly, because we can see the scratches, so it's definitely not zero.
well,
but
well, if the cushion runs out,
Yeah.
then you get the scratches. Yeah.
thud. That's a big cable. Looks kind of like my rowing machine, although, you know.
It's very cute.
We can do another demonstration of the field.
Oh, yes. While you're getting there, so
Yes.
another thing to remember as we're moving these big, you know, multiple 1,000-ton slices of the detector around, one other thing to remember is that the LHC itself is built at an angle, because we have the Jura Mountains on one side, we have Lake Geneva on the other side. The whole LHC is at a slight tilt. And because our detector, for alignment purposes, because we have to be completely perpendicular to the beam pipe, it means that our detector is also sitting at a slight tilt. And I think it's a cup like 1.5 degrees or something where we are. But the important thing is to not think, as you're sliding a slice out, you are going to either be sliding the slice up or down, which will also affect, you know, like the scraping and stuff on the floor, as if you're pulling it up a hill or something.
And you also have to prevent the floating out from
Yeah, exactly.
from the axis. So
But that's
actually,
what they're on rails, right?
these guys are really free floating. Well, a little bit of a rail we already have. It
Yep.
was not always. Of course, this is an extremely complex task to move these several thousand tons of equipment up and down.
Yeah.
I mean, along the beam pipe. That's
It's so cool that we
shouldn't
can do it.
underestimate. Actually, very cool. I remember the
Mhm.
first time I saw it moving. It was still on the surface.
Oh, wow.
25 years ago. I photoed, and I was really really happy with that, seeing that how it works. You know, you can imagine it in a palm size
Amazing.
equipment, but this is really a 4-story building.
That is so cool. That's a huge wrench over there.
That's an M19.
That's that Derek's got that is pretty awesome.
We want to demonstrate. I got to be careful here.
How does it
have
feel when you move that in your hands? Is it like
Yeah, so
whack?
this is a wrench, of course, and it's got some length to it. Unlike the chain, it's kind of one continuous piece of metal. And so the whole thing really wants to stay aligned with the field.
Hey.
But you
Unfortunately,
can,
we cannot simply show or make the feeling how hard it is
Yeah.
to flip.
but as
Can you
Claire hinted
use
at
one
it.
finger, use one finger and like push it around, see, because I want to see how like
Oh,
no,
you
no,
mean
on the to turn it around.
Turn it around,
No, on
try
the-
to
on-
flip it with
Yeah,
the
there you
finger.
go. Flip it with
like this?
yeah.
Yeah.
Okay.
So there's this.
Actually, that's a good question. That why isn't it symmetric?
What?
You see, now it is almost horizontal. When
Oh,
it
yeah.
flips it, will
Flips
be
it.
a little bit. Could you please just flip it?
He's
Yeah.
trying. He's trying very hard.
Yeah, and just release it. You see,
Oh yeah, it hangs down. 'Cause,
I'm wondering about it for several.
Yeah.
minutes.
I mean, is
So,
it not just
okay.
like the gradient of the field?
Of course, that there should
Well-
be physics behind.
It could be a textbook question. So
There
what
we
we're
go.
going to do is
homework for your
Yeah.
class, Catherine.
we're just going to walk to the other side, and this will try to stay aligned with the field that it feels at each point. And we can kind of see how this strong magnetic field changes the direction as we go.
Awesome.
But it is it's too hard to describe the feeling of
Oh,
these
look at
things.
that. Like it's now pointing straight back. It's turning around. That is super
And you
cool.
see, it is tilting down.
And this side, yeah, it hangs down a bit more. We don't know why, but
Huh.
so yeah,
And
it really
up
wants
more,
to
up.
like stay in this alignment with the field, no matter how you hold it. Even if I put my finger there, it's bizarre. It's like a ghost, you know? So, are there other questions while we're down here?
Yeah.
You can also, if you want to see anything about the detector, it's an opportunity to ask us to go somewhere and show you.
I think we have a question at the back, so I'll just change the camera. See there.
Maybe if you come up, we can hear you better on the microphone.
Mm-hmm.
What's the goal for the organizations in the next, say, 15, 20 years?
No, I need you to come closer. It's hard to hear.
What's the goal of the organization seen in like the next 15, 20 years?
I still did not quite catch that. Sorry.
What's the goal of the organizations in the next 15, 20 years?
What's
So
the goal?
of the
Yeah.
organisation, the goal of CERN
Yeah.
in the next 50 to 20 years.
Okay. No, that's also a good question, and that ties into the previous question. So let's go here. Okay, we have the LHC, which is only the latest in CERN's range of accelerators that they've had over the years, and each accelerator has taken us one or more steps further into understanding how the universe works at a fundamental scale. So for example, back in the 80s, this tunnel was actually in use. The tunnel was already built. We didn't have to dig out the tunnel for the LHC because there was a previous accelerator called LEP, which collided electrons and positrons. And with this detector, we were able to discover the W and the Z bosons, so they're the carriers of the weak nuclear force. We weren't quite able to get the Higgs, but that's where the LHC came in. The LHC.
That was quite unfortunate.
It was close. It was super close. And then there was the Tevatron as well, who was the 1 TeV, well, 1.8 TeV.
None of them found the Higgs for absolutely two different reasons.
Yeah.
The Tevatron could find it because the energy was there.
But they just didn't have enough data.
Exactly. The luminosity, as we call nicely. The LEP was very close,
but not
exactly.
Yeah.
Unfortunately, we couldn't crank up the energy any further due to the Bremsstrahlung that topped completely. We were saturated in the energy with the electrons. I know, I was there. That was the reason why we had to build in another detector. If I may quote equations here. As you know, if you put a particle in a circular path, it will radiate off energy.
Mm-hmm.
Some of its kinetic energy is going to be radiated off. That's what we call Bremsstrahlung with this very nice English word. The Bremsstrahlung depends on the fourth power of the particle mass inverted.
Mm-hmm.
So it means that if you use a heavier charged particle,
you get much less
of this radiation taking off. So that means that on the same path, if you accelerate a 2,000 times more heavy charged particle, proton instead of electron, you get something like 10 to the 8 less Bremsstrahlung. That allows you to accelerate the particle further. Here, the limitation is the magnetic field of the dipole magnets, which is scaled with the normal m to the 1.
Of course, we're talking specifically about a circular machine here, because if you have a straight linear collider, then you obviously don't need to worry about the Bremsstrahlung. So
very probably you don't need to. Well, the acceleration itself does something, but of course
you don't have this immense loss due to the fact that you're curving this particle around continuously in a circle.
But on the other hand, curving the particle on a circle has an absolute advantage over the
because you can multiply accelerate it. Exactly. So designing these accelerators is a toss-up between whether you want to have have one go at accelerating, like in a linear collider, but then you get less losses. Or if you want to do multiple accelerations, like iteratively, but then you're going to have losses due to the Bremsstrahlung, as Zoltan was saying. So that's really why one of the main reasons why CERN went from the electron proton accelerator into the proton collider. The other benefit of a proton collider is that it's because a proton is not a fundamental particle, because it's made of quarks and gluons, and there's antiquarks in there, or the C-quarks. When protons collide, you have so many options for combining quarks, antiquarks, gluons, everything. There are so many possibilities, and that's why proton colliders are messy but very ideal discovery machines. Like if you're not really sure what you're looking for, but you want to keep your options open, proton colliders are the way to go.
That's a very important thing. Proton accelerators are discovery machines on the given technological level, while the electron colliders, electron-positron colliders, are the precision machines.
Yeah.
So usually the rhythm of this research field is that we have a proton machine to discover the particles, SPPS for the Zs and the Ws. Then we had a lepton accelerator for measuring precisely the Z boson's physical parameters. And of course, then we had to build again another discovery machine to discover the Higgs boson.
Right.
Now the next step. Oh, you want to talk about the next step?
Go for it. Well, so the next step is the upgrade to the LHC. So still a proton machine, but just allowing us to get much more luminosity, much more data. Right.
Oh yeah, that's going to
but so that's an upgrade to the LHC. But so we're still talking in the realm of proton collider discovery machine. But then after that, we are going to go to what we are currently calling the FCC, the Future Circular Collider.
You might see the planned
layout
here.
This would be amazing. It would be like this, about 100-kilometer long circumference machine that goes under Lake Geneva, goes, around the mountains.
The mountain here.
It's huge.
Almost up to Annecy.
Right. And in this particular case, again, we've got this idea, like we did with the current LHC tunnel, where we could first use it for a precision machine, an electron-positron collider, and then use it in the future for a discovery machine with protons again.
We are talking about the next 100 years.
We're talking about the next 100 years. So like, our grandkids, your grandkids, maybe they will be the ones who work on these things. If things go well with the planning, we could start building the first machine in the 2040s. And maybe be getting
something about 2070.
2070, I think. I don't know if that's like for starting to build the HH, the Hadron one, or more.
I just have to confess something very private. In 2071, I will be 100.
Good. So if your 100th birthday, you can get a proton 100. 100th birthday, you can get a 100-kilometer long collider.
I hope I will be here on the surface and not below.
But the point of having the precision machine is, like, we've discovered the Higgs, right? We know that there is this Higgs. We don't currently know if this is the only Higgs-like boson. But we have discovered a new particle, and there is still a lot of information that we can learn about this particle. So having a collider where, like right now at the LHC, we can create a Higgs boson, I think 1 in every 10 billion collisions. If we build an electron-positron collider where we have tuned the energy so that the energy of the collision is giving us the Higgs mass, we then create a Higgs factory. So we would create lots and lots and lots of Higgs bosons, so many Higgs bosons, which would allow us to study the Higgs boson in impeccable detail. And this is important because it's, you know, it's only when we study something in really, really deep detail that allows us to fully understand the implications of this particle, and that is where you know, future possibilities for use and stuff happen. So yeah, so that is the goal for, you know, the next future collider. And then, of course, after that, after we've studied the Higgs boson to death, the plan would then be to go on to another hadron collider, back to the discovery setting, where we're now looking at you know, a much higher range of energies, because when you are creating particle
It's a snake.
it's a snake. When you're creating particles in these collisions, you have a budget, and that budget is the energy of your collision. So you can only, because, you know, E equals mc squared, so you can only create the you can only create a particle if you have the energy to pay for it. Now, so the Higgs boson, we had to have a collider with LHC energy to have enough energy to produce Higgs bosons. We know that there is dark matter in the universe. We don't know what dark matter is, and we don't know what mass dark matter would have. So there are multiple experiments in the world looking for dark matter at light energies. We've covered like this nice range of energies that we've got up to now, but if there is dark matter that has a heavier energy, we would obviously need to have a bigger, stronger collider to be able to discover it. Hey, I'm not sure if that answered, Kevin, can you check if that was that was good, like a good enough answer for everyone?
Yeah, I think they're happy with that answer. Thank you, Claire.
Cool. Are there any more questions?
I think we have to tell that there are quite a lot of things to discover.
There's a
The
well,
standard
there's
model is
95% of the universe.
exactly. The standard model is being far from being.
Yeah,
a
it's
complete-
annoyingly accurate where we currently are, but it's also far from the
Any
complete picture of the
university on
universe.
any exam, if you could tell only about the 5% of the
Yeah.
topic, you would fail. So we are there.
So I think we've got some more questions actually. Can you raise your hand if you've had a question?
Yay.
Should we start with this side? So I think if you'd like to come to the front and ask your question.
Yay.
This good enough?
Can
Can you hear me?
Yes,
Yes,
perfect.
perfect.
Great. So my name's Dan. I just wondered, how does, if ever, does geopolitical tension affect projects at CERN?
A lot. It affects it a lot. We are a collaboration of 5,000 people, and you know, so we need we need 5,000 people just to keep the detector working, to have people here in the control room to keep the detector running. We need loads of people analyzing the data, making sure that our measurements of electrons and muons are good. And then and that's even before we get anywhere close to doing physics analysis. Not to mention the huge computing resources and everything that is necessary. So because we do rely on so many people internationally, it really does have a big impact when countries or people are unable to do that sort of work. In addition, there's a big there can be big financial implications as well. Like for example, if we use gases, so protodune, for example, is a good example because protodune is a prototype neutrino detector for the Dune experiment, which is going to be built in the US. But what happened was the prototypes are these big 10 by 10 meter like 10 by 10 by 10 meter cryostats that they would fill up with liquid argon. So they had the first run, they emptied out the liquid argon. I think they sold CERN sells the liquid argon back to the companies because it's difficult to store. And then 2 years later, it was in the middle of COVID, and they wanted to, and now they were ready for another refilling to do the second round of testing of their prototypes. And there was a European shortage of liquid argon. Also, the Ukraine conflict actually had a big impact on this as well. So there's tons of liquid argon in the US, but like very, very limited supply of liquid argon in Europe. And this delayed that for a long period of time. In addition, a lot of the chips and the modules and things so right now we're building new detectors for our future upgrades and things, and these are also being affected by the supply of lithium and other things for chip production, not to mention this this DDRM explosion that happened recently. So there's a lot, the budgeting for the project is something that I'm very glad that I've not had to deal with up until this point, because it can be very difficult. Derek, I don't know if there's anything you want to add on that.
I didn't hear, it's a bit hard with my headphones. The original question was about how the collaboration, something to do with money and the collaboration.
It was how geopolitical conflicts affect the work.
Well, I think your answer was quite good, but we could also answer it a little differently. But CERN and these large international scientific collaborations are actually a geopolitical force for good. So when you have this large experiment, this is a scientific experiment that is industrial in scale. I don't think anybody's going to argue that. It requires a lot of money and resources and people power to run experiments like this and keep the facility going. So when a country contributes or they join an experiment like this, they have to literally contribute manpower, resources, money, proportional to whatever they can. There's some rules about this, so it doesn't hurt smaller countries more than larger. But then they're invested, right? And the idea is, and I think this is true, you don't want to get banned from something like this, and also the access to the training for your scientists, your engineers. You don't want to lose access to the return on your investment, basically, by paying into something like this. And so having large scientific collaborations are actually kind of this, they can be maybe not a force for good, but a neutralizer, right? A deterrent to getting involved in some conflict with your member state, because there would be repercussions in what you gain from being a part of this. So this is another way we kind of think of science.
Yeah, thanks.
Here.
That's really important. Yeah.
Mm-hmm.
Yeah. Great question. Do we have another question?
Any other questions? If you'd like to come forward, you in the yellow hat. I'll just adjust the camera.
Yeah, sorry. Can you hear me?
Yeah.
Yeah, so I wanted to ask, what is the recruitment process like? That is one. Good question. I'm going to try and compress it into the same. So, recruitment process, and what is it? Is it remote based? And also, is this lecture going around Europe in European universities? So, I would like to imagine, so maybe countries like Hungary, where they can speak English. So is there a barrier in terms of the culture of maybe doing some of the projects that is demanded? So how is this structured? And also, are you taking students from outside Europe? Do you have access in places like Africa?
Yes, absolutely. So like I said, I'm actually South African. And
so I wanted to ask, how can you move into it?
Right. So CERN operates, it's quite democratic, right? Like you can Derek was talking about this buying into things, and there's different ways that you can do that, right? So first of all, you can become an associate member or a member state of CERN, and that is CERN itself. And in which case, that is your country paying a certain amount of money to CERN, and that goes to CERN's operating costs during the year. In return, CERN hires people for staff positions from their member and associate member states. And also opportunities like to tender for contracts to do work such as digging a new tunnel or building a new building or something at CERN. Member and associate member states are allowed to tender for these contracts. So that's like the payback that CERN gives. Then you have the experiments like Atlas, CMS, and LHV Atlas, and there's lots of them. And the way this works is it's a similar concept, but on a smaller scale. So instead of it being a national thing, it goes to a university or a lab. So a university would decide, like, for example, Lancashire decides, I want to be a member of the CMS experiment. And so this university pays a joining fee to CMS, which covers operational costs and things. And also there's like a kind of a yearly like subscription fee. And as a result, any professors, staff, postdocs, students at your university are allowed to work on that experiment and get full access to the data, basically as much as the university is allowed. It can give them, if you can, to come here, to be here at CERN, to work on the experiment, to go underground and play with magnetic fields like Derek's doing, all of that. So that's on the experiment. So that's on a university side. So for example, myself, I was part of a university who joined the Atlas experiment back in 2010. So I did my PhD in a university in South Africa. I am South African, but because they joined the Atlas experiment, I was able to come over to CERN and work on the Atlas experiment and use that data for my PhD. Culturally, so culturally, it's an amazing place because you have so many people all around. Zoltan, who's sitting next to me, is Hungarian. Derek is from the US. We have some Italians. We have Profila, is that you? I don't know. So we have some Indian people. We have, I don't even know.
Georgia.
Georgia. We have somebody from Georgia. So we have like
very often
just sitting in this control room, we have like 6 or 7 nationalities, and it's really interesting because you get to learn about so many different people from so many different places, and it also, I think, is really important because it like you can sit here and you can have like 4 different languages spoken around you, and I think that's a wonderful type of normality to have. So yeah, I don't know if there's something you would like to add.
Well, I would add that it is nice, like you said, Claire, working with people from all around the world. And it's something that it's just another perk, really, because it's like, although we're in one place, it's like a little bit of every country and every culture is here. And so you get to, I've learned so much, so many different recipes, but better cooking techniques from friends that are from different cultures. And I'm still not a great cook, but I at least, I have access to this. I don't have to.
And people are proud of it. Like if you walk around the cavern, you will often see bits of equipment with like a country's flag on it.
I mean, right here, you can see the flag of Pakistan.
There we go. Yeah,
wrote
up there.
Pakistan.
Yeah, on the. There we go. On.
And right
Actually,
there.
this is a kind of a byproduct.
Yeah.
Being here, that besides the professional things, we learn and admire each other's culture.
Yeah.
That's really funny. I love
You
to be here in
can't
the
work
control room.
cooperatively with people unless you respect like their cultural differences and everything. And it you know, the differences is what the difference in the diversity is actually what brings a lot of strength into the collaboration, because people think of things differently, they have different types of solutions, and you know, it's that diversity that really gives you strength.
But that's a very good place to learn all these things.
Yeah.
I love to be here.
Same. Oh, was that did that answer the question?
Any more questions?
Yes, thank you. Can you raise your hand if you've got another question? So I think if you're on this side, if you'd like to come to the front. You got a question? Okay.
Duck.
Yeah,
Oh,
I'll
flying duck.
go up to get the question and then I'll come back now.
Okay. Derek's playing with a little duck down there.
Yeah, I think we completely lost him. But I was very interested in the snake business we saw. I think we should remake it.
Oh yeah.
We're packing up in the underground. We're going to come up.
All right, cool.
Okay.
Bye, Duck.
Bye bye.
See you soon on the next visit. That goes to Italy in the afternoon.
Oh, nice.
Probably one at a time.
Don't forget the wrench.
Oh yeah.
No. We've got everything.
Good stuff.
Don't forget anything in there.
No.
There we are. Hello.
Hi. Catherine.
Hello. Just got the question from the student. So they asked, because of where there's 4 different detectors on the LHC ring, firstly, what are the sorts of things they detect? And secondly, what are the differences between those 4 detectors?
Oh, great. So, Atlas and CMS are general purpose detectors, by which I mean those detectors are designed to catch everything, or as much of everything as possible that they can, that is coming out of the collision points.
They're literally like a clamshell around the collision point. We're trying to contain it all in there.
Right.
Yeah.
Exactly. And the reason why we do this is because since it's general purpose, we're trying to catch everything. So Higgs bosons, for example, which decay in certain ways. We also want to study like W and Z bosons to a high precision, which decay in certain ways. Then we also want to leave things open for, you know, potential discoveries of dark matter and things that we don't know about. So as a general purpose detector, the point is to be able to cover as much of the space, this 4 pi region around the collision point as possible. So that's Atlas and CMS, and they are located opposite each other on the ring for the exact reason that to be fair and democratic, the LHC needs to be able to provide the same amount of collisions to each of those detectors. And the way that to do that is to have them, you know, opposite each other, so they can make the same amount of collisions happen, you know, opposite them. Then we have Alice and LHCb. And if you look at Alice and LHCb, these pictures here, the most striking difference that you'll notice between them and Atlas and CMS is that they are asymmetrically built. So Alice and LHCb have, oopsie.
Sorry, my fault. Okay.
Zoltan's fighting with the slideshow, yeah. Alice and LHCb have very specific physics goals. Alice's main goal is actually not to study proton-proton collisions, but to study collisions of lead ions. So when you smash lead ions together, which we can do in the LHC, and every part of every year they do this. When you smash the lead ions together, what actually happens is in the quarks inside the the lead ions kind of dissociate, and you get this formation of a superfluid, which we call the quark-gluon plasma. And this is akin to what the universe was like in the very, very first seconds of the universe. So Alice's goal is specifically to study what this quark-gluon plasma does, how it, everything about it. And so they've built their detector specifically for studying the quark-gluon plasma. But the upshot of that is that it's not very good for detecting Higgs bosons and things like that.
Yeah.
Similarly for
Maybe-
LHCb. Oh, yeah. Do you want to
Maybe
show
I
them
could
something?
interject just real quick while we're passing by this picture. This also shows, you may have shown something similar on the screen, I'm not sure, but this shows all of the different accelerators that we have at CERN over the years. And a lot of them we still use to this day for other experiments. Now, Claire is right now giving you a comprehensive explanation of the 4 main experiments that we have on the LHC around the Large Hadron Collider, but we do have many other experiments at CERN that do not use the Large Hadron Collider, like the antimatter decelerator, where they make antiprotons. I can't even talk about all of these, but they're labeled here.
Isolde
But yeah.
Medici, yeah.
There's so many, yes. So a lot of
target
science
errors.
goes on here.
Yeah, the north
Okay.
area is fixed target. They often use that for like testing. So, if we're building a new detector, then we would do some beam tests in the north area. Going back to LHCb, so LHCb's physics goal is to understand how antimatter differs from matter, specifically in quarks. So so when you have particles that are made from quarks, whether or not the conservation laws apply, whether or not there is CP violation for antimatter. So again, because LHCb has a very specific physics goal, they have built their detectors actually got a much higher precision tracking than ours do. As a flip side, it means they can't handle the amounts of radiation we get. So LHCb actually gets far less collisions than Atlas and CMS does. But the flip side is they have a higher precision on the tracking and so they're able to look into very specific certain particles and how those certain particles decay. So that's just like a brief overview. Like, we've got 2 general ones which are there to be able to take as much data as possible, withstand as much of the radiation from the collisions as possible, and to catch everything. And then we have 2 high precision detectors which basically ignore the rest of the stuff, but are there to give us a lot more information about particular types of physics.
Great, thank you both. I think we have another question at the back, so I'm just going to ask the student their question and I'll come straight back.
Cool. So Derek and Noemi are back to the surface, and so they will be heading out soon and rejoining us here in the control room.
Of course, there will be radiation reactions in between. So this is the leftovers or these particles are stored, and if it's in an environment,
Hello again, hi.
Hi.
The student question was because of where radiation is produced as a result of the particle collisions. Firstly, what happens after the particle collisions in terms of like remaining particles? What is done with those? And then secondly, what's the environmental impact of the radiation?
Lovely question. In fact, Zoltan, I know me about radiation experts for our detector. By far, the place that gets the most radiation is the collision point. So, and this is just because this is protons that they collide, and we just have the most number of particles flying outwards in this in the smallest amount of space. As a result, our detectors that are closest to this collision point have to be built with things that can withstand high amounts of radiation. So this is why we choose silicon detectors. The electronics and stuff also have to be very radiation hard. And yeah, now remember, most of the particles actually move through the tracker and then get stopped in the calorimeters. So that's what happens to them. They literally get stopped and turned into a spray of particle of energy. Muons end up traveling through the detector, and then after a little while a muon will decay, because that's what muons do. While the beam is running, while the collisions are happening, nobody's allowed inside the cavern. And because obviously that's just too much radiation. Also, there's also radiation produced just by the circulation of the beam and everything as well.
But sorry for interrupting.
No, this is your expertise.
So, and we are talking about much larger radiation, whatever. It is not like at the reactors, fission reactors. So we are many orders of magnitude less radioactive. If we are not allowed people to go in, it is rather a legal thing. So you definitely, what I want to say, that if you would happen to be on Derek was in the cavern, you would not die. However, you would get much higher dose than the legal limit allows.
Yeah.
Obviously, we have to obey the rules. That's very important. So I just would like to be very clear on this, that this is not a killer machine.
Right.
However, there are some places, the very forward region,
that's shielding,
next
that
to the
aren't
beam,
shielding
exactly,
that Derek showed us.
or in the tunnel,
yeah,
where it is not healthy to be there. That's why we have very, very strong rules, very stringent rules to prevent of any human being there. If you would break through the doors, Derek was very kind not to show the way, but I'm pretty sure that if you would be there in that situation, you would immediately figure out how to break through a door. But if you would break through the door when the accelerator is running, it would immediately result in shutting down the complete accelerator complex, all the 27 kilometers. Why we don't have so much jokes about it is that we have cameras everywhere. So
we know who it was.
We know who it was.
And you would get in trouble.
Exactly.
The red door that was down there that goes to the tunnel, the LHC tunnel. Yeah, I think if you were to even start to open it, before the second it's like cracked open.
In November, they did that. Somebody did that in the SPS, in one of the smaller accelerators. They opened a door that was interlocked, and they dumped the LHC beam.
Dump the beam immediately, and there'd be
made a lot of chance for you to
sneak in there. Obviously, we don't want to get on the front page of any newspaper just because of this. We have many other things with that, why we do want to be on the front page of physics, but not of this.
In terms of environmental impact, so being built underground, actually, this was not even the primary reason why the tunnel was built underground. It actually, the main reason the tunnel was built underground was because it actually cost less than to build it there and buy the land at the surface. But being built underground does also mitigate some, or help with the environmental impact. But in addition, a lot of I think Derek actually mentioned this as he was entering, how you can't really take equipment in and out. Your camera, the cell phone and stuff was fine, but there are very strict regulations on taking equipment out of the cavern. So many stages, like you have, even to take a power supply out of the cavern, you actually have to put it in a set of door, like an area where it does a scan to see if there's any residual radiation on it. And even at the entrances and the exits to every single CERN site, there is a detector, a very sensitive radiation detector, so that will send an alarm and call the fire department the certain fire department if
Mhm.
if it detects that you
I was
may have
told,
some
yeah,
radiation.
and I was told a story, I forget by who, maybe Andreas, but somebody had thrown away something that was a little bit radioactivated, not much. But it was in the trash, and then it was in a garbage truck, and the garbage truck was trying to leave the gate,
Oh,
Mhm.
and
yeah,
it set off that detector.
Yeah.
It was able
Yeah.
to detect that this was in the truck,
yeah.
and so the truck remained, and then they threw the trash.
Everything is
Fine.
logged.
So actually, being an international organization, in principle, we are not depending on the country's regulations. However, we work in a very strong connection with the host state uh, authorities, both the French and the Swiss. And in addition, they have their own measurements as well. It totally independently from our lab. With Noemi, we just walked on the countryside in between Switzerland and France, and we saw those detectors that are
Yeah.
not belonging to CERN at all. So
Yeah.
we cannot hide anything. Actually, we don't even want to.
No.
But we couldn't hide anything, and we definitely want to behave correctly on this, because this would be very loud if we would.
In fact, because CERN is an international organization, in most cases, I think if not all cases, you know, everybody has to agree, which ultimately ends up meaning that we have to we conform to the strictest
Mhm.
of the requirements that everyone has.
That totally applies on the radiation
Yeah,
rules. I know these rules, and these are extremely strict.
Yeah.
Yeah. Obviously, there is another aspect of this, that whatever trash we produce, we have to export out from our territory, and that will end finally in the host state somehow. So definitely, we cannot do any tricks on this.
Yeah. Yeah.
That's very important. But if we are at the radiation, I just would like to remind that those radiation levels that are, for example, at the tracker or all over the experiment, we always have to design our equipment such that it survives. We have to choose the material in accordance with the expected activation, the expected radiation damage. The electronics must survive. The polymers should not fall apart. Even the iron that we use should not activate up so much that we wouldn't be able to work correctly.
In fact, the LHC has performed so well over the past 10 years, 15 years, whatever it is, that both the pixel and silicon strip track, like inner detector, like the first layers of each of the detectors have passed their limits, their design limits. And we're keeping on going.
They're in pain.
They're in pain,
but
struggling, but
they're still
we're
working.
gonna make it.
Yeah,
We'll
yeah.
limp over the finish line in June, but we'll make it.
So this is a very large portion of our work.
Yeah.
That we have to design everything accordingly to.
And remember, all of this was based on technology from the late 90s, early 2000s. Like that's when these things were built, right? Like it's not just the latest technology. These things were built in 2000. So
that's right.
Do we have any last questions?
Oh yeah, many. That's so good to see.
I'll come back.
The question is, how common are accidents in the down in the detector cabin?
Very uncommon, if at all, especially downstairs.
So we never had any radiation related accident yet.
Yeah.
That's
You would first want to say what kind of accident, because there's engineers working down there with tools, and so they could potentially drop a tool. And
we have those.
That's why you wear
accidents.
safety boots, so you don't drop it on your toes.
Yes, exactly.
That's why we have those kind of accidents that a normal industrial site has. Also, of course, we try to avoid them as much as we can. So again, the safety rules are very strong. We apply people just for safety. They are our policeman, actually.
I think the thing is, like, somebody tripped over a piece of grass or something. My worst
that
accident
happens.
I've ever had was I was on call and it was 4 o'clock in the morning and I got a phone call. I was at home, got up out of my bed, sleepily was talking on the phone, walking down the stairs, and I misstepped. I missed the last 2 steps and I like landed, rolled my ankle. So I was on like, yeah, didn't break anything, but
The dangers of being on call.
the dangers
See
of being
that,
on call.
But no, I don't
Exactly.
think any radiation.
No,
I don't know. of
I
any
don't know about
radiation
any
related.
I
radiation
know
related
there was one
mechanical.
at Atlas many, many years ago. Somebody had been working. This is many, many years ago now. I think it was at point one, and he'd been working with stuff, and a little piece of something had fallen down into the cuff of his pants,
Mm-hmm.
and he went like finished his work, went home, but he didn't realize this, whatever, got home and everything. And the people were doing an accounting and they realized that something was missing or whatever. But by the time they got to his house, he was already, radiation sickness and all of that.
Oh,
But as a result, this is where like a lot of these, I think that, but this is why we have all of these things at the exits and everything now.
What-
This was many, many, many
yeah,
years
what
ago.
we have to say that based on any accident, we always revise after any accident.
there's
We
a
always
big
revise the
investigation.
safety, exactly, the safety rules.
Yeah.
And if needed, we tune them in order to avoid this. Just like anywhere else in industry,
Yeah.
we are
Around other labs as well. I remember
Exactly.
Fermilab in the US, when you go into a radio activated area, there's a test beam, you go in to get your equipment. It could be radio activated for a short period of time. When you come out, there's a procedure where you have to be not stripped, but scanned
Yeah.
completely.
we also
head to
have
toe.
hands-feet
We also do that,
monitors.
yeah.
The reason why Derek didn't use them now is that before opening the detector for the serial technical stop, the
You
very
were
first,
scanned,
exactly,
yeah.
I was member of the team. It is always a rule that the first team who goes in is an RP team with radiation detectors, and we check all the key points, and we also take smear tests, so we can be super sure that there is no radiation in the cavern.
You go in and check everything ahead
Exactly,
of time. and
exactly.
clear it, basically.
And in addition, you had to wear your personal dosimeter in case we know that there is a bit elevated radioactivity in a given zone. We require people to take their active dosimeters as well, and that we immediately read out. That has an alarm function, has never
Yeah.
set off
Yeah.
anyway. But also we have an alarm function on, so we can immediately monitor if something happens. Are really strict on. I don't make any jokes of. No.
Anything else?
Okay, great. Thank you very much. I think it's probably a good point to round off now. So we just want to say a huge thank you to Claire, Derek, Zoltan, the rest of the CMS Visits team. I think the students have done
Thank you so much, everyone. You've been a great audience and amazing questions.
Yes.
Kept
It
us on
was
our
our pleasure
toes.
to participate. This was
Yeah.
today. Yeah.
Thank
You
you.
are-
And
Thank
You
you.
are young, so if you want, there's social media pages for our experiment where we
Yes.
post updates on new results and stuff.
Exactly.
go.
Follow those.
Exactly.
Yeah.
and hopefully we'll see you at CERN one day.
Yeah.
Yep.
See you then.
All right. Have a nice
Bye-bye.
day.
Bye.
Bye bye.